Okay, so I wanted to start by showing a really great app that I found through the AP Calculus teachers group that I'm a part of. Somebody suggested that they were using this app called A Little Calculus. It was 99 cents and well worth it. So I can go in here. We're going to show the disk method. I can come in here and put in like a function. Let's see. Well, I'm happy with this one. So I have x squared minus 3. And we're going from -1 to 1. Let's go from, yeah, we'll just stay from -1 to 1. And so that's what it looks like right there. But I want to go back to, sorry, not that. So back on the disk method. Sorry, I hit the wrong key. All right, so this is a graph of what I have in here, which is x squared minus 3. Okay, and we're going to rotate it around the axis of rotation is y equals 1.6. So let's go around the axis of rotation. Let's go around 2. Y equals 2. I'll add that in. And let's look at our picture. All right, so since this is the disk method, it's going 2 minus x squared minus 3. All right, now what I want to show you is this is really neat. All right, so this is our figure cut up into rectangles. So you can see the rectangles, maybe if I blow it up some, you can see there's rectangles there. But I can actually turn it on I can let you see the discs and what this looks like if we divided them up into all these different subdivisions. So it's pretty neat how we can really look at it and we're actually adding up discs. Now, since they're paper thin, they won't have this like jaggedness to it. But right now, these are just sample. Let me see if I can get it back at the beginning. I'm trying to get it vertical. Almost. It's too hard. So anyway, if you look at the red at the bottom, you see that we've got these sample rectangles that have revolved around the line y equals 2. Let's do another one. Let's do just x squared. Okay. And so we have x squared, and let's go around the y equals 0. All right, so now we have this right here. If you can envision that going around the line y equals 0. Just imagine if it's going around the line y equals 0, there would be no gaps in it or anything, and it would look sort of like this. Let me blow that up a bit. Where we've got all these rectangles that are going around, and it makes this figure. Of course, we would have lots and lots more discs than this. I just started playing with this morning, so I don't know if I have. Oh, we can do more subdivisions. Great. So let's do 50. Okay, awesome. All right, so we get a lot better picture of what's happening here if I do 50. Let's move this. Isn't this great? And so we see all these discs that I'm adding up. They come into the center and go back out. If we look at it on the side, that's what it would look like on the side if I rotated this. It's really actually a marvelous tool. Let's see what else we have here. Show cross sections only. All right, so those are our cross sections that we're going to divide. And so it actually shows just the cross sections. And then we're going to rotate those. So we'll see what other choices I have here. Show one disc only. Let's turn these off. I don't know where it went. Hang on. Oh, that's not good. Hopefully we can get it back. Show region of rotation. Okay, show one disc only. I'm not sure what that does. Show axis of rotation, and we don't really need it in radians. And now all of a sudden it's not working. Wow, don't know what that's doing. So let me turn off some of these. And see if we can get back where we were. Oh, wow, that's interesting. All right, so let's pull this down here. If I pull it down, I get different shapes. It's like a spool. As it rotates around, it's thicker in the middle now. And all of these rectangles, as you revolve it around, makes discs. So each one of those is like a rectangle. All right, let's do a washer method. And so here I can change the line that we're going to revolve around, but if you can imagine revolving that for a minute around the axis. Let's look at this. There. Okay, so we get all these washers as it revolves around. There's some of them are smaller than others. It gets bigger. It's like at the very beginning, close to on the y-axis. It's closer together than at the end when it's really far together. And so this is a great visual. If we look at it this way, we see our rectangles, but that's like a full rotation around. So it's really cool to look at. So let's change it a bit. Right, so let's make our function, this function, let's make this x squared and see what happens. Okay, so we have this figure going around and it should have changed a bit. Well, it's not changing very much. Here, let's move this up. Let's see, I want to keep that. Let's move the axis of rotation up to 0. Let's see what happens here. So we get this cute little thing. Okay, right at the very beginning, it's a disc because it's touching what it's revolving around, but everything else is washers, so I would treat it as washers. Isn't it great to be able to see what happens as you revolve that around? It's really cool. Little shape here. And we're adding up all of these washers that are like donuts. I mean, I could go on and do this forever. While I'm here, now these are rotations. Notice these are revolving, and so I don't already have the figure in the white part that shows you the eventual figure when you rotate it up here. But let's also look at cross sections. Now, it's like I was telling people, the object is already made. And so what's happening is this is the base of the object. We'll make a more interesting base later. And popping up out of it are, let's do squares. And let's see what it makes. This is so awesome. So coming up out of this figure is already made for us. Nothing's revolving, nothing revolving. This is just an interesting base, and popping up out of it are squares. Which I should be able to expand that. So coming up out of it are all these interesting squares. There's one right at the very face of it, and squares are coming up out of it. There's a good picture. So squares are popping up off of that base at us like this. So now I can also choose something else. Let's have semicircles coming up out of it. And let's look at that. Let's see. All right, so let's see what this looks like. So this is our base, and semicircles are popping up out of it. And so all of these are, we're adding up semicircles with a radius of f of x. So these are cross sections. It's already made. It's already sitting there like that. And this is the base. All right, let's get a more regular base. Let's say we have y equals, let's say, I was going to do square root of x. I'll try x to the 1/2 power, and that ought to give me a square root. All right, and then y equals 0. So I have this as a base, and it's already made. Something is, if we were in class together, I'd be pointing like up into the air. This is already made. It's like a loaf of bread, I guess. This is the base of it. Sorry, I can't get it right. Anyway, I can't hold it still, but that's the base of it. And it looks like this. Wow, it's very unwieldy. There, that's kind of better. Okay, so as I maneuver it around, we can see that popping up out of it are semicircles. And we're just adding up these semicircles. And it makes this interesting kind of tunnel looking thing. Let's let something else come up out of it, like let's do equilateral triangles and see what it makes. I don't know why it's still moving around. I guess it moves on its own, so I'll just let it go. So it has, this is a base, and popping up out of it are equilateral triangles. Let's see if I can get it. There it is. All right, so sorry, let me shrink it down. There we go. So what is popping up out of that base is equilateral triangles. This is a good view right here. Because it has a nice, cool edge to it. Sorry, this is hard to manage. There we go. All right, so popping up out of it are triangles. And they get smaller and bigger depending on where I am in the figure. So it's really, really interesting thing. But again, this object is already made. It's not made by revolving. Okay. All right, so we'll play around with that some. It'll give us like a way to look at things. Okay, now I wanted to do a couple of examples. I think I have a fun snowy picture here. Okay, so an example that I wanted to do for you just to kind of clarify some things that we talked about today that seem like y'all had questions on. I was actually right now doing an example out of the book. So this is example 4 on page 462. So we're given all these boundaries, y equals x squared plus 1. I got to think if I want to do this in terms of x or y equals 0, x equals 0, and x equals 1. And we are going about the y-axis. So right now, if I want to go around the y-axis, I need f of y's, which means I eventually need to solve all of these for x. So I'm going to have y minus 1 equals x squared. So x equals plus or minus the square root of y minus 1. All right, let's see what in the world this looks like. Well, first of all, I'm actually going to graph it using this because I'm more familiar with it. And x squared plus 1 looks like this. Y equals 0 is the x-axis. X equals 0. Sorry. X equals 0 is the y-axis. And x equals 1 is this vertical line over here in green. Let me undo that. Yeah, that's okay. I guess we'll do it this way. All right, now we are taking this. Now this is a revolution. Let me read the words. It says revolved around. So this object, this is not the base of the object. This is not a cross-section problem. We're going to actually revolve this around here and make some sort of object. All right, now first of all, as this green swings around, it'll make just a solid cylindrical object as it goes around. But then I want to come back and carve out this inside, and it'll have kind of an interesting, almost like a dog bowl or something. All right, so I'm going around the y-axis, so make sure you know that. And so until I teach you something called shells, if you're going around the y-axis, do an f of y or solve for x, because I'm going this way with my disc or washers. Now, one reason I'm doing this is this is flush up against it. And so I'm actually going to do 2 regions. I'm going to do this region here around and just make a cylinder. And then I'm going to do this region around with washers. The reason that I'm doing it in 2 regions is because it switches to this graph at 1. All right, so this bottom region is not even a washer. The bottom region, as it goes around to the other side, region as it goes around to the other sides, the bottom region is just going to look like this. Sorry, I didn't do that very symmetric, but let me try again. So as it rotates around and you get this solid figure, the bottom region is not washers, it is discs. All right, so I'm going to do the bottom region, region 1. As the integral from, and I'm going up the y-axis. And so I'm going to x squared plus 1. So I'm going from 0 to 1. And on the right is this, which is the line x equals 1 minus 0. So I'm doing right minus left. I'm just going around the y-axis, so all I've got to do is say x minus 0. So this is going to be x minus 0 squared dx. All right, then I'm going to go from 1 to wherever these intersect up here. All right, now those intersect at the point where x is 1. If x is 1, then it intercepts this quadratic at 2. So I'm climbing up the y-axis, and so I'm going to go to 2. Now I'm going to have washers, so I need some room. So my next region is washers, and I have this. Right minus left, right minus left, right minus left. And I hope you can see my pen, right minus left. Let's do it in yellow. All right, so you have right minus left, right minus left, right minus left. Hopefully you see that. All right, but you have to do the outer squared and then the inner squared. So what we're doing is this. That usually means it's going to freeze. Sorry. See if I can come back into it. Hope we didn't lose it all. Let's see if I still have it back here. All right, so there it is. All right, so what we have is this. This is x squared plus 1, and this is x equals 1. So I'm doing this part around first and making all of these rectangles swing around, and it just makes a big base that's cylindrical. Now, this is washers, and so I'm going to go 1 minus 0, and then I'm going to subtract out the curve minus 0. So I'm doing line minus, line minus line. It's going to give me this length right here. In fact, it's going to be 1 minus 0 for a length of 1. And then I need all these x distances here that I'm going to subtract out. So my washers, I'm going to have line minus line, which will be 1 minus 0 squared. And I'm doing just this top part right here. So let me talk about that again on this slide. So from 1 to 2, y is 1, y is 2. I'm going to revolve this around. So I'm saying 1 minus 0 squared. And then I'm going to say this minus this squared. But I have to do it in terms of y. All right, so I have 1 minus 0 squared. And then the inside part is this curve, which is the square root of y, minus 1, which is my x distance. And it's plus or minus, but I only need the plus. And so then I'm saying this distance minus this distance, so I get minus 0, because I'm just going around 0. All right, so I have the integral from 1 to 2 of 1 squared plus the square root of y minus 1 squared, which is just y minus 1. wait a minute, I made some sort of mistake. Sorry, I didn't set that up right. I did too much explaining. We'll go to this picture. So I'm going to have two regions. The integral from 0 to 1. I'm going to go pi r squared dy. All right, I think I even forgot my pi, but as much as I've preached about that. This part is going to be 1 minus 0. And so this whole distance is just 1. Then I'm going to add on all of this. And this first washer is going to be 1 minus 0 squared. And then this part is going to be the square root of y minus 1 squared, dy pi r squared. And I'm going to go from 1 to 2. Oh yeah, and I can't move this up. All right, so let's do that. I feel like I've done a bad job of explaining this because I think I over-explained it. Sorry, I'm just going to erase all of that and redraw it. Just to reiterate it again, I've gone this far on this problem. All right, so we have something like this going around the y-axis. It's not too bad to spend all the time on this problem. This is 1. This is y is 2, because that's where this intersected x squared plus 1 intersected y equals x squared plus 1 intersected x equals 1 when y was 2. All right, so up until 1, you just have 1 minus 0. It's just a disk. This is a washer, so you have 1 minus 0 squared. And then we solve this for x. We had plus or minus, but all we need is the plus distance, this x distance going across. So on this other part right here, the inside part is going to be right minus left. So this x distance is the square root of y minus 1 minus 0, which is set up down here. All right, so then I'll go and work this one out. You have pi integral from 0 to 1 of 1 squared dy plus the pi times, and don't forget your pi. See, I almost forgot mine today. This part is 1 plus this part is y minus 1 dy. So it ends up not being too hard to do. I feel like I should have a plus in here. Just a minute. Oh, sorry. I'm messing this up all over, but this is good. I'm okay. And that my mistakes can help you. This is washers. I wanted to subtract out. I wanted to carve out all of this part as it revolves around. All right, so this should have been minus right here. All right, so I have pi, follow your variable y from 0 to 1, plus pi. This is the integral from 1 to 2 of, this is 1 minus y minus negative 1, so I'll get 2 minus y dy. So this part is going to be pi times 1 minus pi times 0 as I fill these in. This region down here, shouldn't be using all the same colors. Don't forget your pi. And this one's going to be 2y minus y squared over 2 from 1 to 2. Let's carry it up here. This part is just pi plus pi times 2 times 2 is 4 minus, that'll be 2. Don't neglect filling in 0, or I'm filling in 1 actually. So it's going to be 2 minus 1/2. So I have pi plus pi times 2 minus, this is 1.5. So I have pi plus pi times 0.5. And so I end up with 1.5 pi, or 3/2 pi would be the volume of this shaped figure that we probably should maybe try to type into my really cool app. All right, so to talk about the setup again there, because the setup is everything. So talking about the setup again, since I made 2 mistakes on this late Friday afternoon, I'm going around the y-axis. We'll talk about what would happen if I was going around another line while we're at it. And then there's something really important, so don't tune me out. Just stay with me for this moment. All right, so you have x squared plus 1, but it's only bounded by, in here, let me shade it in like this. All right, so we have x squared plus 1. We have x equals 1, x equals 0, and y equals 0. So we had all of that. And so this is our only bounded part right here. And so we don't need the other part. Sorry, I'm taking a lot of time on this problem, but it's time that I normally would have spent in class. All right, now I'm going around the y-axis, and so I need these x distances. This distance is right minus left, and so it was 1 minus 0 up till I get to 1. 0 to 1 of pi r squared dy. Then I hit this next region that has a different shape in it. So I'm going to do the outside. I'm doing washers. Squared, squared, dy. So this top part is still 1 minus 0, and this bottom part is this x distance minus 0. My x distance is the square root of y minus 1 minus 0 squared. All right, this part ended up being pi y from 0 to 1. This part was pi from 1 to 2. I'm not going to continue on because I just worked it on the other slide. But remember this part of it. Let's remember what it became before I erased everything. I should have just gone to another slide before I erased it. That part was, let's see, how much was that? I had, oh well, we'll do it. It was like something with a half in it. Okay. So this part is 1 minus the square root of y minus 1 squared, which gave me pi integral from 1 to 2 of 2 minus y dy, which gave me 2y minus y squared over 2. Don't forget your pi from 1 to 2, which gave you pi times 4 minus 2 minus 2 minus 1/2. So this is what I couldn't remember. This is 2 minus 1.5. And so this was 1/2 pi. And so this part must have just been pi. Right, now the reason I wanted to go back to this is if you take this part and rotate it around the y-axis, you actually just get a big cylinder. So actually you could use geometry for this part right here because you just get a big cylinder. All right, so how would you find the volume of a cylinder is pi r squared h. The height of this cylinder is 1. The radius of the cylinder is 1. So you could actually have done a cylinder plus this other piece that wraps around like that. All right, sorry, that took a while. All right, now I'm going to do, so sometimes you have to do 2 regions. Now I'm going to do one that is going around a line. So I may have done on your homework number 21. So, but let's do it. All right, 21 is x is equal to y squared. X is equal to 4. And it says the word revolve, so it's not a cross section. We're revolving around the line x equals 5. All right, revolving along the line 1, 2, 3. X equals 5 is like the y-axis, so we need an f of y until you learn something called shells, which we never really have to learn, but I'll show it to you in case you ever want to use it. All right, so we're going around the something like the y-axis, so we need an f of y. So I'm going to square root this, and I get y equals plus or minus square root of x. Chances are I don't need both of those pieces, but we'll see. Hang on just a minute. So sorry, my husband's just starting his meeting too. Let's see. Okay, so sorry, I'm changing my view. You can see what you see, and I've lost it. There it is. Okay, so now we have x is equal to y squared. You get 0, 0. You get 1, 1. If you have an xy chart and you fill in 4, you get plus or minus 2. So you have this. I don't know why I dotted it. You have this and this is x is equal to y squared. So I do need both of them. Here's the line x equals 4. And so this is going to be washers because we're going around the line x equals 5. So we're going along this line right here. All right, so it's not touching the line, so we're going to have washers. All right, so the easy way to do it is you're going to go right. You're going to set up your washers. I'm going to do it in terms of y. Also, watch this really carefully. I see the symmetry of this kind of nose cone thing. So I actually am going to not go all the way down here to revolve it like over here. It'll make it kind of like a bead actually with a hole in the middle if you can envision that. But what I'm going to do is I'm just going to do this part of it around here, and then I'm going to double it because I'm convinced of the symmetry. So I'm going to double that. Now let's get a different color. And I kind of wished I hadn't put that highlight in. Okay, so I'm going to double it. All right, now I'm going to go line minus curve, right minus left. So I'm going to say 5 minus this x distance because I want to lose that part and just get this length right here. So this length across is 5 minus the square root of x. Remember, I'm doubling it. And I'm only going to go from 0 to whatever this intersection is, which x is 4, so it'll go to 2. All right, then I want to subtract off the inside, which is going to be green. So to subtract off the inside, I'm going to say 5 minus 4, 5 minus 4, 5 minus 4, which obviously is just 1. So I'm subtracting out the inside. All right, so now let's work this one out, because I think I looked up the answer to this. This gives me 2 pi, because I'm doubling it to get this part down here as it goes around. All right, so this is 2 pi, integral from 0 to 2 of 5 minus the square root of x times itself.
Can you guys hear me?
It gives me 25 minus 10 root x plus x. So I have 25 minus 10 root x plus x, and then this is going to be minus 1. And I want to stay on this slide, so in case we need the picture. All right, so I have 2 pi, don't forget about your 2 pi, from 0 to 2 of 24 minus 10 square, oh, I'm sorry. I need this in terms of y, because I'm going sideways. So what did I have? Oh, I had x equals y squared. Let me set this up again. Boy, I'm making a lot of mistakes this afternoon. I need it in terms of y. I need a right minus left. So here in white, let's see. Again, these not so bad that I've messed this up. It gives us good discussions. All right, so this is going to be 5 minus this, which is y squared, which is going to make it a little bit easier anyway. So this part is 5 minus y squared, because this distance is x, and this distance is x is equal to y squared. I could have left it like that. And then the inside distance is still 5 minus 4. 5 minus 4 is still the part you're subtracting off. All right, so that's going to be easier, because I need it all in terms of y, because I'm going from 0 to 2. All right, so this is going to be 25 minus 10y squared plus y to the 4th minus 1 from this. So this is 2 pi, integral from 0 to 2 of 24 minus 10y squared plus y to the 4th dy. So this gives me 24y minus 10y cubed over 3 plus y to the 5th over 5 from 0 to 2. This gives you 48 minus 80 thirds plus 32 fifths. Don't neglect filling in 0, but it makes all of these 0. Now, this would be a non-calculator problem, so I need a common denominator of 15. So 48 times 15 is 720, if I did that right. And this is going to be times 5, so I guess that's 400. And this one I'm going to multiply by 3, which will give me 96. So I have 720, 496. So I have 1216. And I still have to multiply it by 2.
No, I was gonna say.
This seems way too big.
You're in.
I don't, oh, I forgot about the minus. Okay. Wow, I've made a lot of mistakes. I'm so sorry. I forgot to subtract this. All right. Watch out for all my Carol's mistakes. All right, so 720 minus 400 is 320, and 96
How many is that? How many?
is 416 times 2. 12, 832. So all of this multiplied together at the top is 832 pi over 15. And I'll double check that later and come back and say again if I've messed it up, but I think that's right. 21 was not that hard. All right, so to kind of just talk about what happens with a figure, I did this on the last one, but suppose you had something like this. Let's do it in green. And then in red. Okay. And so you have this region enclosed. Okay. And let's say if you're going around the y-axis, so I'll make that black. So say we're going around the y-axis. Okay. So I would have washers. I would have red minus 0 squared. So red minus 0 squared. And then I would have on the inside, I'm going to subtract off. Don't forget your pi. Remember how many times I've said that, and I almost just did it. Then we want to come back and scoop out this green minus 0 squared, whatever's the green. Okay. Now, what if we wanted to go around this line? X equals -1. So what would we do is we would go red minus -1, curve minus line. So we would say pi times red minus -1, and that makes good sense because we really want to stretch it out, minus green minus -1. So if the line that you're going around is in front of your curve, like over here, you'll go curve minus line. What if the line is over here, like this? Then to find your values, you would say this minus green and this minus red. So the outside would be line minus the green curve squared, and then line minus the red curve squared. How does that make sense? If my line is over here, how does that make sense as far as a washer is concerned? Something with a hole in it, as the rectangle rotates around a line and makes a washer. All right, so how that makes sense is these are x distances right here. As we go up and fill in y dy, we get these x distances. But we don't want those x distances. We want these lengths. And so say this is 7. All right, so if x is 7. So this would be 7 minus whatever these x's were. And so we want this distance, like all the way across here, we don't want. We want this minus the distance you came out, or up if you're doing it in terms of y.